Okay, so good afternoon, and today we are going to continue a little bit with functional programming, and in particular, yesterday we started to talk about functional programming, and I said that in functional programming the emphasis is on pure functions. A function is pure if it has no side effects. So basically, typically when you call the same function twice, it's going to return the same values and produce no side effect. Typically, mathematical functions are examples of pure functions. So how do you program in functional programming style when you don't have the possibility to modify values, you don't have state? So actually this is one of the most difficult things to be done in functional programming. And I go back to this post by Bartosz Milewski, which presents a functional data structure in C++, which is the list. So this is a typical implementation of a list that is going to be functional. This Bartosz Milewski is an expert in C++, in concurrency, and in Haskell. Haskell is a functional programming language. And he's also the founder of a company that is producing software using Haskell and functional programming. So I think he's the best guy to try to explain us what is functional programming and what is the main aspects of this kind of language. And in particular, he starts this post by saying that data structures in functional languages are immutable. And so what does it mean? That you cannot really modify an existing data structure. Now this, as he says, sounds as an anathema. It means how can you actually program, so transform data if you cannot modify state and variables? So yeah, so this is basically because we are our background when we started to study programming was imperative languages, in which the program is written as a sequence of operation on variables. So it's the typical von Neumann model, in which you have data structures and then you have operation on these data structures. So according to the classical imperative programming, a program is just you take an input, then you prepare an initial state, and then you combine the state with the input. You continue to transform the state step by step until you produce the final result. Functional programming instead is different, because functional programming, you look at the program as just a one big function, which from input you produce output. So it's like a sort of very complicated large function, and there is no really any state inside, because you are just transforming input into output. So you have to find a way to combine functions that transform input into output. So in that case, you don't need to modify an internal state. And in particular, he says, are you telling me that I can't change a value stored in a vector, delete a node in a tree, or push an element on a stack? Well, yes and no. It's all a matter of interpretation. When you give me a list and I give you back the same list with one more element, have I modified it, or have I constructed a brand new list with the same elements plus one more? And the answer is, why would you care? Actually, you might care if you are still holding on to your original list. As that list changed in a functional language, the original data structure will remain unmodified. the version from before the modification persists. Hence, such data structure are called persistent, and this has nothing to do with being storable on a disk. Okay, so in this post, he presents an implementation of a list, which is a persistent data structure. Okay, and why persistent data structure are better? He says that are better because they are easier to reason about and maintain, and they are thread safe. And this is going to be important when we are going to start multi-threaded programming in C++ 11. They can be implemented efficiently, and they require some type of resource management to garbage collect them. So let's look at the example. I think we already did this example, but we are going a little bit going again through it in more detail. So I'm going to skip all the blah blah. And so this is the list. So a list, first of all, the definition in English. A list of T, where T is a template, is either empty or it consists of an element of type T followed by a list of T. So a list is the typical recursive data structure because you can define it as a base case, which is the empty list, plus a recursive case, which is T followed by another list. Okay, so basically this definition translates directly into a generic data structure with two constructors, one for the first case, the empty list, and another one taking the value list head tail pair. So empty list and the general definition, which is recursive. See, list is defined in terms of another list. Okay. Now, here's the trick. Since we are going to make all lists immutable, they cannot be changed, we can guarantee that the second argument to the second constructor, marked in red, is forever frozen, so it's not going to change. Therefore, we don't have to deep copy it. We can just store a reference to it inside the list. Okay, this is a key point. So you don't need to copy all the elements inside. You can just store a pointer to the rest of the list. So you need to store an element, which contains the value, plus a reference, or a pointer if you want, to the next list. Okay? So whenever you create a list, what you really need is a value and a pointer to the next list. Okay, so let's go a little bit more into the implementation. So the value is going to be stored into a structure that we call item. And this is actually the internal implementation of the list, so it's private. It's not visible from the outside. And then we are going to store a pointer to an item which contains the value that we call head. And of course, how this is structure done? Well, the structure is a value plus a pointer to the next element. So it's a simple implementation of a list. And of course, we can also check if the list is empty. And if the list is empty, is initialized with a null pointer that is not going to change because it cannot change. And so we return not head to check if it's empty or not. Finally, when we construct a list as a value plus another list, we are going to create a new item which contains the value and the pointer head of the tail list, which is stored into next. So head will point to the new item. And inside the item you have next, which points to the next element. So quite simple. Okay, Then there are a few functions like front to access the first element, so it returns the value. And remember, this is constant because we are not modifying the list. And pop front, which returns everything except the head, so basically the tail of the list. And again, this is constant because we are not modifying the list, but we are returning a new list. Okay? And here you have one more constructor, which is written here, explicit list item, const item. And this constructor is private because can only be called from prop front, cannot be called from the user. And it's used just to make a list containing just the tail. Okay? We also use assertion. We cannot have the front when the list is empty, and we cannot do pop front when the list is empty. So we assert, and if this assertion fails, your program will exit with error. Okay, that's not very clear. Maybe drawing an exception is more appropriate. I don't know. Anyway, there is nothing much we can do about that. Finally, if we want to access the list from different points, and most importantly, if we want to delete a list, because at some point we have to free the memory, one nice way of doing that is to use reference counting, and in particular to use shared pointers. So instead of just using a naked pointer in the definition of the list here, and do a new here, we are going to use a shared pointer and create a shared point there. So basically several lists can point to the same element, and only when the last list goes out of scope, the memory is freed. So a shared pointer, we just create the shared pointer in the constructor, and in struct item, we just have a shared pointer to the next, and the shared pointer is also passed to the as a reference, const reference, into the constructor. Okay, and there is not much else to change because the rest of the functions are going to stay the same. This is going to stay the same, this is going to stay the same, and so on. So let's look at the implementation now. So I just downloaded the code from GitHub. It works except this initialization here that in C++, in GCC doesn't work for some reason. It doesn't see these RBin and RN for some reason. Anyway, this is just implementation. So we have the structure item, which uses shared pointers. Then we have the explicit private constructor that is going to be called from the pop front. Then we have list with the two constructors, the function to check if it's empty or not. Then we are going to have a function for accessing the first element, the head, and the function for accessing the tail. We have a function for adding one element. Actually, this produces a new list, which is equal to the previous list, to the current list, but in front you find a new element. And this is the implementation, just a pointer to the first item. Okay, and then we can define a few functions that act on the list. I'm going to discuss very briefly because then we are going to implement a simple program with this list. So this is fmap. Fmap takes a function f and a list, and it produces a new list which all the elements in the list lst have been applied the function f. So basically this fmap applies function f to all elements of this list, producing a new list and the function f is expected to take a t and produce a u. So first thing we do is to check that f is actually a function that takes a t and returns a u or something similar. So this is done by checking that f is convertible to ut. Okay. Then, if the list is empty, we just return the empty list. Otherwise, if the list is not empty, we return a list that consists of the function applied to the head, and as a tail, fmap applied to the remaining list. So fmap is a recursive function. Here we have the base of the recursion, and here we have the recursive rule for solving the function. Okay, so look at these neat programming techniques. First, the static assert to guarantee that function f does the right thing, and this is checked by the compiler. And then the recursive implementation of fmap. Something similar is done by filter. So filter takes a list, it applies a predicate that is a function that returns a boolean, and returns a smaller list t that contains only those elements of the original list for which the predicate is true. So the implementation is quite simple. Again, first we check that p is actually a predicate on t. That means that a function that takes a t and returns a boolean. And then we do the base of the recursion when it's empty, when the list is empty. Then, if the predicate on head is true, then we produce a list that contains the head element, the front element, and as a tail, filter applied to the tail. If instead list front is not true, we return a list which is just the filter applied to the tail. So we do not include front. So again, this is quite interesting. Then is an accumulation function. It takes an initial value of accumulation, which is for example, suppose we want to sum all elements of a list of integers. Then we pass here 0, and this accumulates all the result and returns the results here. So basically, it applies a function to all elements of a list, and the result is summed into accumulation. So first of all, again, we check that f is a function that takes a t and a u and returns a u, so it provides the accumulation. And then if it's empty, it just returns the same value as before. Otherwise, it returns f applied to the front and the accumulation between all the elements in the tail. Okay, so again, recursive. And fold is the same thing, but it's done by using a left recursion. That means that instead of doing this, which is simpler, we actually do this, which is a little bit more complicated to understand, but not too much. So basically, fold does the tail recursion. So it starts from the last element and goes up to the first element. Then for each applies a function of void to all elements of f, and this is done for non-pure functions. Like, for example, if we want to print on the screen, then we have to apply a function that actually takes t and prints on the screen without producing any visible result. And this is the implementation for concatenating two lists. Okay, now that we have this, why don't we use this data structure for implementing a simple program? So maybe we take some confidence with programming in a functional programming language. So let's do the implementation of the sieve over a toasted. That is, we want to compute the prime number within between 2 and a certain upper limit, for example, 100. And as I said, we want to compute prime number. So I start with making the program, the main program. What we want to do is to start the sieve over a toaster works like this. We take a list of all integers between, for example, 2 and 100, and we start eliminating all the multiples of 2, so all the even numbers. Then the next, after 2, the next is 3, so we eliminate all multiples of 3. So the next that remains is 5, so we eliminate all the multiples of 5, and so on. So the idea is that every time we produce a shorter list which contains all, at the end we will just contain all prime numbers within 2 and 100. Okay, so let's start by generating a list containing all numbers between 2 and a certain limit. Suppose the limit is 100. So how can we produce this? Well, so I'm going to write a function which will produce a list of integers, and I call this function range. And range will just produce what we need to produce. So basically, prime numbers, all numbers between a certain low element and upper element. So suppose we want to start from A, we want to go up to B, and we want an interval of delta. So this is like the MATLAB range function or the Python range function. Okay. Okay. So we are going to have a recursive definition of range, of course. So what we do is that if A is already greater or equal to B, okay, then we return an empty list. Right? Because we are not generating any number. Generate is a list that contains as first element A and as a second element A plus delta, B delta. Okay? Do you agree? Questions on this?
Okay.
Let's start from 3 up to limit. We'll just generate all the non-odd numbers between 3 and 99. And so this is a list that starts with 2, then 3, then 5, then 7, and so on. Okay? Now, if it works, so let's write a print function. Okay? For writing a print function, we are going to use the same trick that is proposed by in the blog post. So we are going to use the for each function. So we are going to do this. So this, we want to print this list. Then we do for each. Remember, for each applies a function to all the elements of a list. Now, the function of all elements of a list, it's here. It's embedded. It's a lambda function. It's a function that doesn't use any global variable. It just takes v, which is an element inside the list, and it's going to see out the element within parentheses. Okay, and then it prints an NL. Actually, I want to change that a little bit because I want to do a slightly different so I'm going to use separate all the elements with commas, and so we just print in it. Let's see if this works. Okay, so it prints just all the odd numbers, 2 followed by all the odd numbers. Okay, now we need to eliminate all multiples of 3, then all multiples of 4, and so on. So we have to, let's do it first sequentially, and then we are going to write a recursive function that does this. So how can we eliminate all multiples of a certain number? Well, the idea would be that we use the filter function. The filter function is going to produce a new list that we call without tree, that is going to eliminate all the multiples of 3 from the element. Okay, it must be 6, 9, and things like that. So we want to eliminate all multiples of 3 from list init. So this is not yet the Eratosthenes, okay? So we are just going incrementally. So let's look at the prototype of filter. Filter takes a predicate and a list. So we first have to decide the predicate. So we write it again as a lambda function. So we have to check if this is multiple of 3. So if is multiple of 3, we return true. So we do if the remainder of the division between v and 3 is 0, then it means that it's divisible for 0. So we have to return false. It's not to be included. If instead is not divisible from 0, then we return true. So we just from 0. And we apply this to init, and then we print init, and we print, sorry, forgot the semicolon. Okay, so here, I don't know if you can see, I'm going to enlarge a little bit and running again. So the first list contains 3, 9, etc., 15. The second list doesn't contain the multiple of 3. Unfortunately, it doesn't contain 3, so that's not the right approach, of course. We cannot eliminate from the entire list all the multiple of 3. We have to eliminate from a partial amount of things. And then we have to repeat also, because then we have to eliminate all the multiple of 5, all the multiple of 7, and so on. So we have to do that recursively, as always. I'm going to write a function as this. That receives an initial list and produces the list of integers until a certain limit. So how does it work? So it first tries to, of course, check if LST is empty. And as always, this is the base of the recursion. And if the list is empty, we return as a result an empty list. If it is not empty, what we do is that take the front, okay, and we try to remove it from the list, the tail of the list. Okay, so what we do is that we need this code to be generalized, and so that here we can pass any element. We do this as another function that takes an integer and a list and produces a list which is just the filter. Okay, so basically it's the same as filter. Okay, so it takes list and returns another list where I've removed all the multiple of m. Okay, so what we do here is that we have to return a list that contains the first one, which we know is prime, and as a tail we return what Eratosthenes applied to what? To remove multi from list, in which we pass LST front and LST pop front. So we have a list in which the first element is already prime, so we return. The remaining is we take the list the tail, we remove all multiples of the prime number, and we obtain a new list, and we pass this new list to Eratosthenes. Okay? So now we can try to okay, I hope I didn't make any mistake in writing. Okay, I did, and sorry, I have to cut. So m is not part, is part of the environment of this lambda function, so I have to pass it there. Okay, so here we have the original list, and this is the list of primes, and it should be correct, hopefully. Okay? So it works. There is a lot of recursion, as you can see. There is Eratosthenes, which calls Eratosthenes, that calls remove from list, and so on. So there is a lot of recursion. Let's see if this approach can scale. For example, is this a very slow approach or not? So we first check the argument. And then if this is okay, then we define limit as okay, and then we execute. So now this program takes as a first parameter on the command line the limit we want to achieve. What I wrote, oh, I forgot here, star. So if I run, it doesn't run because it wants a limit. So 100, it prints everything. I don't want to print too much, so I'm not going to print. Just print the final list. So this is 100, 1000. To understand how much time does it take to run this program, let's use the time function on of Unix, which measures how much time does it take to execute the program. So the actual user time is it's less than 1 millisecond, so it's not really visible. And if I search this, then this is 20 milliseconds, more or less. If I go up to 10,000, it takes a little bit more than 1 second, which is a lot. So this is not a very efficient program, I would say. And after a while, you will see that unfortunately this crashes because the recursion is a little bit too heavy. Yeah, so with 30,000, it requires a little bit less than 7 seconds. I did some try yesterday, if I remember well, after 50,000 it crashes. Maybe this time it crashes less before. Okay, 4,000 still okay. Yeah, with 50,000, it takes more than 60 seconds. So, I mean, in general, is not the most efficient way to implement these kind of things. If you implement this by using 4 cycles, it will take much less, because Eratosthenes is also a quite easy algorithm. So, where is the overhead coming from here? So, the overhead is coming from, first of all, from recursion, because C++ is not a language that is optimized for recursion. And the other very large overhead actually comes from memory, because there are a lot of these very small shared pointers around. And here. And and they are all linked one after the other in a chain. So when the program finishes here, and you have to get rid of this, and also of this, it's going to decrease the reference counters, and it's trying to deallocate the memory. It will actually take a long time, because it's a lot of very small memory, it's a lot of reference counters, and every reference counter is accessed with an atomic instruction, which is a little bit heavy. So actually, nothing really difficult about the algorithm, but a lot of overhead comes actually from managing these shared pointers. It's also important to understand that the numbers are there just once. So there is not a lot of memory used from this program, because the two lists, init and prime_stu, actually some elements. Okay. If, for example, you look at the remove from list, a filter, and if you look at filter, the filter doesn't actually create any new element. It just creates this list objects that are passed around and moved, and the representation is moved here and there. So the actual overhead of filter is not in creating the actual elements, but in creating these list objects, which are very small. They just contain a pointer, but still they take some time to be created and destroyed. So all these temporary objects. Okay, so I think we are ready for having a 10 minutes break too now. And, when we come back, we are going to look again at MetaSim for the project.
Senta, volevo sapere.
Sì,
Mi sente?
sì, sì.
Ma volevo sapere, ma in questo esempio della lista con i tempi, ma è possibile, cioè se io avessi tanti thread che lavorano sulla lista, no?
Sì.
In questo caso non avrei nessun tipo di problema che succedano dei danni.
No, esattamente, proprio così.
Cioè, se uno provassero a creare tipo 10 thread che lavorano sulla lista, mettono elementi, levano elementi, tutto, non
In
succederebbe.
realtà la lista non viene mai modificata, vengono sempre create delle copie locali, per cui, come vedi, vediamo un po' se la riapro. Cioè tutte le funzioni della lista, le funzioni pubbliche, sono tutte definite come
Sì, sì.
possibile modificarla. E una volta che uno ha creato l'oggetto lista, quell'oggetto lì è immutabile.
Sì, sì.
Quindi i vari thread non possono farsi casino, possono solo leggere e fare delle copie.
Ok. Per cui di fatto io, in realtà, se io avessi tanti thread che lavorano su quella lista, io avrei tantissime copie della stessa lista.
Ogni thread si fa i conti sulle sue copie. Poi, al momento di mettere tutto insieme, tutti i calcoli tutti insieme, a quel punto probabilmente bisognerà,
Ah.
eh,
Cioè,
diciamo, fare qualcosa, però non è difficile, cioè alla fin fine il thread produrrà un output che sarà le liste parzialmente, le liste dei risultati parziali. E
mm,
poi eventualmente ci sarà un thread che aspetta che tutti abbiano finito e poi prende tutte queste liste di risultati parziali e li mette insieme nella lista finale.
sì,
Per
sì.
esempio, ecco, la lista non è magari l'esempio più
Sì,
calzante perché è una struttura dati poco efficiente, però in generale potrebbe essere
sì, sì.
una struttura del genere, sì.
Ok. Il problema però potrebbe avvenire se le varie liste, perché alla fine quelle liste sono liste di puntatori all'oggetto che te scegli di avere, no? Per cui volendo potrebbero accedere tutti a un elemento, poi di fatto.
L'elemento, se l'elemento viene condiviso e tu modifichi l'elemento,
Però
la lista è immutabile, però gli elementi che sono contenuti dentro
quello...
potrebbero essere mutabili, quindi
Sì, sì.
lì bisogna stare attenti a
Sì, sì.
quello che si fa, però chiaramente non dipende dalla lista.
No, infatti, se tu implementassi anche quegli altri oggetti come immutabili, allora a quel
Esatto,
punto...
esatto. Quindi diciamo non è tanto il C++ non fornisce meccanismi di linguaggio per fare queste cose,
No.
e deve essere il programmatore a costruirseli.
Sì,
Per
sì.
esempio, noi ci siamo costruiti questa lista immutabile, perché se no il C++ tenderebbe a farti fare quello che ti pare.
Sì.
Però la cosa bella del C++ è che è un linguaggio molto malleabile, per cui se uno vuole fare programmazione funzionale con qualche restrizione, però più o meno ci riesce.
Sì.
E il compilatore acchiappa un sacco di errori. Non è, diciamo, un linguaggio funzionale, però simula almeno alcuni degli aspetti
Sì.
con, con delle tecniche di template, utilizzando molto il const, le reference, eccetera, eccetera, si riesce comunque a essere abbastanza efficienti.
Sì, sì.
Do you have class here?
Yes, another hour.
E la casca funziona.
Excuse me, professor. Professor,
Yes.
can I ask? Can I have a question? All the three students from GPCSE from
Yes.
Trento. We would like to ask if it is possible to have the 9 credits course instead
Mhm.
of 6, because in our study plan your course is 6 credits for us, but we were wondering if it is possible to have the 9 credits course to change.
I think you have to ask the.
Claudio Manfroni.
Yeah, but I think he has to go through the committee because I don't know. I don't think it's possible to change these things very easily. So for a PhD, it's easier because it just goes through the committee and that's it. And for you in Trento, I don't know. I have to ask.
Okay, I can
So
ask.
I will ask. Yeah, you and me, we both ask to Claudio Manfroni. Let's see what happens. Okay.
Okay, thank you very much.
No problem. Uh, we start again and we talk a little bit again about the assignment. And as you remember, the assignment is that you have to simulate a set of nodes that communicate via wireless. Okay, and the wireless channel is shared among all nodes, so there can be collisions. And so basically, I would like you to implement this property of collision and possibly collision avoidance. And in the MetaSim library, there is already a very, very elementary skeleton that starts to organize the structure for simulating an Ethernet. So it's not a fully complete model, it's just a skeleton. But you can start from there for implementing your own simulation model. So I would like now to go there and look a little bit at the structure of data examples and discuss that with you. So first of all, if you want to look a little bit at the documentation for MetaSim in a more structured way, you can use the Doxygen program. Doxygen is just a set of scripts that analyzes the HPP files and produce HTML or LaTeX documents, and so it's useful for generating documentation starting from code. And so MetaSim is already configured for that, and in particular there is a file which is called Doxy file, sorry. So if you open this file, Doxy file, you will see several configuration options. So the configuration options are like this, and you can modify, of course. And one that you have to modify is the output directory, because I think that in the repository there is also still the very old path. This output directory. If you want a more helpful way of configuring this file, there should be a program called Doxy Wizard or something like that. But you have to install it. Also, you have to install Doxygen. If you are on Linux, Ubuntu, you can do it with the usual apt-get install Doxygen. Okay, and you can also do Doxy with Doxy. And run Doxy Wizard, and you open your Doxy file here. And then you can go and look at all the different configuration options. There is not much to configure anyway. You can also just change the output directory here in Expert, and then after you do that, you just run everything, run Doxygen, and once that it's finished, you just show the output in HTML format. Okay. The most useful way of looking at it is to look at the class, and this is the class index, and then there is this class hierarchy. Okay. And the class hierarchy, as we have discussed already, the most important classes for modeling are event and entity. Entity is basically if you want to have an object that wants to be part of your simulation, it has to derive from entity and re-implement functions new run and end run, which are the two that needs to be implemented. Okay, and basically a new run is called at the beginning of every simulation run, and the end run is called at the end of every simulation run. Then your entity will have some events that has to be posted and will be triggered, and most of the simulation work happens into events. So basically what an event is just a class, and there is a virtual function called doIt. When the event is triggered, doIt is called, and you have to do some work in this doIt. So one way of programming it is that you actually derive a class from event and you implement the doIt function. For example, last time we have seen the examples, the queue. And this is how it was done. There was a class source, which derives from node, which itself derives from entity. And inside the class source, I defined a class produce event, which derives from event. And I implemented the doIt function, which just calls the produce function on the node, on the source node. Okay, so it's a quite straightforward way of implementing an event. You derive from event and you overload the function doIt. Now, most of the times, this is always the event, the doIt function inside the event will just call a function on another entity. So it's going to call a function basically. Now, to avoid just writing a class when you have to do an event, we introduced a template mechanism for automatically generating this code. And this is called gEvent. So gEvent is templatized with respect to a class on which you have to call a function. Okay? And then when you initialize the event, you have to specify a priority. And there are two public attributes, which is the object and the function that is going to be called. And now you don't need to write any class. When you define an event of type gEvent of a certain class, the doIt is automatically implemented here for calling the function that you just specified. Okay? So let's see if we have an example of this inside this ATH. Here we go. So this event, node event, is just a receiving event for this node, and then there is a send event from this node. When we create a node, we are going to initialize these two events by passing the function that needs to be called. So in the constructor or node, we write register handler receive event. This is the object we are going to call, and then the function to be called is onReceive. So when the receive event is triggered, it's going to call function onReceive, and when the send event is going to be called, it will call the onSend event of this node. Okay, and what are onReceive and onSend? OnReceive and onSend are defined here, and they are just two functions that take a pointer to the event. The event was just triggered. So that's it. So instead of writing a class event and overloading the doIt function and register handler in the constructor, and from now on, every time this event is triggered, is going to be to trigger to call a function onSend. For example, in the new run, I post for the first time the send event by passing a random variable, and so when this is triggered, the onSend function is going to be called. Okay? So it's quite simple. It's actually works, the simulator works like this. Internally, there is a queue of events. And this queue of events, whenever you post an event, the event itself is inserted in this global queue. And the queue is ordered by increasing triggering time. So what the simulator does is to look into this queue for the first event in the queue, the one which is more imminent. Then it's going to take to pop it out from the queue and do the doIt function for this event. So this doIt function will call some function on the entities. Most probably, this will also repost the same event into the queue at a later time. And after all this finishes, the simulator goes back, looks in the queue at the first event, and continues like that. And this until a certain time has elapsed. So the whole simulator cycle is just look in the queue for the next event, process the event. Then look into the queue for the next event and process the event, and so on and so forth. Okay? Events are put into the queue, and they are ordered by time. But what happens if you have two events at the same time? Well, if you have two events at the same time, there is a field inside the event, which is called the priority, that you can set. So you can get this priority, you can set the priority, you can restore the previous priority if there is one. Okay, so the highest this priority, the more urgent is the event, and so the sooner is going to be processed. Okay. The library also provides you with some random variables, and I'm going to show you. Here we go. So random var is a base class which generalize all random variables, and then you have a few specialization, like you have delta var, which just produce always the same value, so it's actually a constant. Deterministic var will just take numbers from a sequence, so it produces a deterministic sequence of numbers. Uniform var produces a random number between two values. It's distributed uniformly. Then exponential var wants an average for the exponential. Generic var, it just you have to specify a generic distribution as a discrete sequence of values. Normal is the Gaussian, Pareto, Poisson, and so on. So you have several distributions here that you can use for your own program. So the simplest one is actually uniform, so I recommend you to use uniform variables in your simulation if you want to use it. It's possible to produce a trace of what's going on. I recommend you to use this trace ASCII, which just prints the events that are happening on a text file. And so you can understand the sequence of events that are going on in your simulation just by looking at the file that is going to be produced. So you can see this as a sort of log. Then you can take statistics, for example, average time, minimum inter-arrival times, things like that. And this is done by using this base stat. And the base stat, you have stat count, which just counts the number of occurrence of an event. Stat max is going to measure the max value of a sequence. This is the average value. This is the minimum value. This is the percentage of occurrences of an event. And this is the square mean of a certain statistic. So you use that for doing your statistic on your specific thing that you want to measure. I'm going to show you how to do that in a while. Okay, so now let's go to our Ethernet implementation. So I started by defining the concept of node. So this is a node that is connected to the network. And as always, the node derives from entity, because I want to have this new run and run. Then it contains a pointer to a network interface that is used for sending out packets. Then it has an interval, which is a random variable for sending out packets. And then it has a vector of nodes to which it wants to send packets. It has two events, receive event and send event. Send event is an internal event which is arrives with a certain interval, and it just produces packets to be sent. I can get the pointer to the net interface. I can set the net interface. I can add node. This is going to be put into the internal vector. I can set and these are the functions that are called by the events. So this is when a message has been, when I receive something, and this is when I send something. And then there is the implementation here. And as I said, initially I just put a random event into the queue, and the time at which is going to be put is randomly generated from this interval. And then this is quite simple. This is this is all very similar, and let's see what happens when on send. When this event is triggered at this specific time, we are going to call on send. So the simulator is going to call this on send. So this on send defines two variables. One is between 100 and 1500. The other one is between 0 and node size. So the first one decides the length of the packet in a with a uniform distribution, and the second one decides to which node I'm going to send this packet. And okay, then I is just n get. So I extract one element from this uniform distribution, and I put that into I. Then I print something on the screen. Then I to have some length, and by this, which is the source, this other one, which is the destination. Then the net interface, and after that I just enqueued the message for sending. And finally, I just same event in the queue at this time, this is the current time, plus a random interval. Okay? So this basically periodically, I would not say periodically because the period is not fixed, but with a random interval, we just send packets to a random destination, and the random destination is selected here. Okay. Very old code. This has been written by me and my friends more than 15 years ago, I would say. So you see there is a lot of very old ways of uh, writing C++ code. For example, this auto PTR now has been deprecated and is substituted by unique pointer. So one thing you should do is to use unique pointer instead of auto pointers. And also this naked pointer here is not very nice. Again, it would be much better to use unique pointer or shared pointers for sending the message. So it's not very nice. You probably need to work a little bit to make it cleaner. What else? Well, if you continue to look at and analyze this code, it's not very difficult to read. So net interface is something that implements the queue towards the Ethernet link. So Ethernet interface is just a specialization of a network interface, and you attach a net interface to an Ethernet link, which realizes the shared channel. So the net interface is what is on the node and implements basically a queue of messages to be sent, a queue of received messages, and a queue of blocked messages, the message that could not be sent because, for example, there was a collision. And then a few variables for the state. For example, backoff is the backoff period, and this counts the number of collisions and so on. It also has an event. It's an event that has to do with the transmission. So it's a transmission event. What else? Then a few functions. The protocol here. So the Ethernet protocol is actually here. Okay? So here is where collision are handled and things like that. When the transmit event is triggered, it's going to call Ethernet interface on transmit. And in the new run, I just clear all the queues, if there are any, so that I'm clean. And the reason initially the transition event is not posted because I don't transmit anything if the queue is empty. And instead, remember that the node, at some point when I want to send, I do net interface send with a certain messages. So let's see what happens when I send a message. So when I send a message, I push it message back on the queue. If the queue has length 1, it means that's the first message. So I start a transmission right away. And this happens with the transition event process. Process is like post, but happens now, right now. So transition event is not actually put in the queue, but is processed immediately. And so basically, the on-transmit is called directly. And what it does is that if the link is busy, it's like having a collision. Otherwise, I call a function of the link, which I call link contend, which is going to work and to see what happens when I contend on the link. After some time. And this after some time depends on the backoff period, depends on another thing, but anyway, I'm going to post the same event later on. Okay. Okay, the link content will do something. So I'm not going too much into details. So you can study and analyze this kind of thing. And when the message has been sent, then we just take it away. We reset the region. We reset the backoff. We, if the queue is not another packet to be transmitted, and so I do transition event process again. Okay, and then you can continue and look at the code and try to understand how it works. It's not very difficult actually. And let's see now the main to see if we can understand how to set up the experiment. So in the main example.cpp, I have a statistic which is collision statistic, which is going to measure the amount of collision I'm going to have. And you have to attach it to an Ethernet link. Okay? And the Ethernet link has an event that is called collision event and to add this statistic to collision event. In general, to events. So whenever the event is triggered, first it calls the do it, and just after completing the do it, is going to call the, and in particular is going to call this probe, which just one event of collision. So it actually counts number of events. So whenever collision event is triggered, it will call the probe, which will record one, that means one collision happened. Okay? This is the main in which I create the simulation. So the three nodes, I had destination node, blah, blah. Then I create an Ethernet link, three Ethernet interfaces, one for each node. The collision statistic, which is attached to the link. And then finally, I do the simulation. And the simulation is like that. I'm going to actually do the simulation many times. So I'm going to use this variable between min and max with a certain step. And I'm going to L1 6 multiplied per average length divided by u. And this is actually the value of the sending interval for the three nodes. So how often they send, basically. And u, it's a measure of the load I want to generate. So between a minimum load and a maximum load, I'm different variables as uniform between 1 and L1 for sending the packets. And then I do the run. I do 5 runs for this certain U, and then I'm going to write all statistic out on a file that later can be used for doing the plotting. So this file is of type new plot output, and it's initialized and it's written. So as output, I'm going to have a collision.txt, measure the number of collision, and actually also writes u. So for every u, I'm going to have the number of collisions, and the average, and the I think the variance. Okay. So the simulation is done many times. Every time I do 5 runs, and for every 5 runs, I'm going to compute the average numbers of collision and the variance on the number of collision, and this is written on the output. Let's see if this compiles. Actually, I didn't really check it. We are inside queue here, sorry. So I had a few deprecated, auto PTR is deprecated, so it did a lot of warnings. It's deprecated, but it should work. So, and here I have the runs for the different U. So for every U, I have several runs, and the output is on collision.txt. 12.6 collision with this variance and this. Okay, so the number of collision varies with this parameter. So my suggestion is that you study this example to see how it works, and you start from here for modifying it a little bit. First, for example, you could try to avoid using auto PTR and substitute with unique pointer. So you do a little bit of refactoring, and then you try to extend this to take into account the fact that we don't have an Ethernet link, but we have one common shared channel. That the nodes have a distance, and so not all nodes can interfere with each other. And the net interface has to take into account the distance when we check for collision, and so on and so forth. So my suggestion is you start from here to build your simulation model for a wireless system. Do you have questions? From now, no, maybe?
With the operations, in the sense, we don't need to use mutex or, for example, for the.
No. This is going to be a sequential program. Okay. So in the assignment, I'm going to. Yes, also because the simulator has not been designed to be multi-threaded. Okay. And actually, these kind of simulations are very difficult to make it multi-threaded. Okay. And the reason is that typically you need one shared queue. And the shared queue is a bottleneck for multi-threaded programming. So you don't get any advantage in actually doing multi-threaded programming for discrete event simulation. There are many papers in the literature and not many practical solutions. Because basically in the simulation you have a sort of global state. And so going parallel is very difficult because you need to modify the global state in a certain order. And to guarantee the order, basically it's like resequentializing again everything. So this is going to be a sequential program, no mutex, no parallel programming. Okay?
Okay, thank you. This section is sequential. We were checking. Nothing happens.
Okay, so if you don't have any other question now, yes.
For you said the routing is not important, but how make the send message between the different nodes?
So yeah, what I suggest to do is that you keep in the model you keep a sort of global data structure where you keep all the nodes that you have in your simulation, and use a simple geographical routing, let's say. So basically, in the node you are going. So in the message you are going to write where you want to send, and from there you understand which is the next node in the route. So I don't want you to implement a routing protocol, because a real routing protocol is going to be quite difficult. So if you want, if you have time after the exams, you can expand the simulation for implementing a routing protocol. But right now, just do something very, very simple, like use two coordinates, x and y, which are logical coordinates. And so, for example, node 2, if it receives a message from 1, is going to send to 3, and if it receives from 1, is going to send to 3. Okay? So if it's, let's say, coming from horizontally, then it goes horizontally to the right. If it's coming vertically, it goes vertically to the south.
Okay.
So very, very simple, okay? Nothing...
Professor, what about the hiding terminal problem?
The hidden node? Sorry, I didn't get it.
The hidden terminal problem, the third problem.
You know what is the hidden terminal problem?
No?
So I'm going to explain. Sorry, this is Spanish. Spanish is probably... So this nice figure that explains you what happens. So you have 3 nodes, A, B, and C. And B is in the range of A, and B is also in the range of C. But A doesn't see C, and C doesn't hear A, because they are not in the same range. So the range of C terminates over B, and the range of A terminates over B. You see? Now, suppose that A wants to send a message to B, and also C wants to send a message to B. So what happens? That A first listens and doesn't hear anything, so it starts sending. Then C starts listening, but it doesn't hear anything because it's not in the range of A. And so he also starts sending. The problem is that B can hear both, and so B is going to have a collision. So even if A and C can listen, they don't hear the other one communicating and then start transmitting, and unfortunately B is going to be into trouble because he hears both A and C. So for A, C is a hidden terminal that can interfere with this communication, and then cannot do anything about it. Did you understand?
Yes, but if this problem happens, we just to lose the packet, or we have
Yes.
to send it again. We have
Yes,
to
yes. So I want you to take this into account, of course. I mean, first of all, this has to happen in the simulation, right?
Okay.
Because I mean, it's not very easy to simulate this kind of things happening.
Yeah.
But depending on how you write the program, you can have this kind of problem in your model or not. So the idea is that you have to show that your model captures this kind of behavior. Okay? The second thing, is, of course, you cannot do anything about it. There are techniques here, and you can find maybe something here on Wikipedia, or you can look at research papers on this kind of things. But I don't want you to resolve this kind of things, of course. No? I just want you to simulate and show that these things can happen. Okay? So I'm not asking you to solve the hidden terminal problem, of course. I want you to simulate it.
One channel for yes, but only you are in the matrix. Only you can only reach the nodes up to you, to the left or to the right. Yes. Of course, wireless is fast. No, but pay attention. If you are too far, nodes are far. They cannot. They cannot share the channel, but they cannot hear each other.
Okay, so if there are not any questions, I think we can stop here, and tomorrow morning we can continue. So if you have questions, please make a list, and tomorrow I can respond to all your questions.
A quick question, Professor.
Yes.
For the hidden problem, we can assume maybe at the beginning two nodes are far and so they cannot reach each other, maybe to solve it, because the hidden problem happens because we have only one channel, we
Yes.
share only one channel, and of course two nodes too far, they cannot hear each other.
Yes.
And maybe if we establish, we decide a range, for example the circle in the figure,
Yes.
maybe we can solve this problem. We know at the beginning which nodes cannot hear each
Yes.
other.
Yes. You know, but in a real setting, it's very difficult to compute the radius. So it's in a real settings you cannot really solve this kind of problem except by using a protocol like slotted mechanism or things like that, in which you reserve slots for communication, so you avoid collisions altogether. But in a collision environment, there is no real way of solving it, especially when you have multi-op. And I want to point out that the final simulation that I want you to do is actually a multi-op, in the sense that I say explicitly that each node has in its range only the 4 immediate neighbors. Okay? So if this is true, then node 1 can only communicate with node 1, 2 and node 2, 1. And node 2, 2 can communicate with both, and the one that are just below and the one that are just to the right. So on node, for example, N1, 2, there's going to be a collision between 1, 1 and 2, 2, which they don't see each other, but they can interfere on node 1, 2. So here you have the hidden terminal problem, yes. And actually, the goal of the simulator is to show how much this impacts on the final communication by measuring the number of packets that are actually received as a function of the number of nodes and to the frequency of sending packets. So I don't want you to avoid the problem. I want you to simulate the problem and to show that this is a problem when you increase too much the frequency. Okay? So for example, one way to try to reduce the impact of this problem is to randomize the sending time. If you randomize the sending time, you are diminishing the probability that is going to be interference between A and C. Of course, you cannot achieve very high throughput, but that's very classic in a setting where you don't have slots, you don't have anything, you just have open collision.
and then from the statistic we can figure out how this problem
yeah, for example, you can figure out a sort of limit throughput
okay.
for that specific system, right?
Okay.
I just want to show that in the here, the larger the range, the more collision you are going to have. So having a large range may or maybe not be a right thing to do. So here I'm just fixing the range. But if you are interested, you could also try to make the range larger and see what happens when you have a very large range.
But here you say all nodes shares one single communication channel. So no matter how far the two nodes are, and if one sends a packet, then the other can hear the channel is busy.
But yes, but this depends on the communication power. So if they are very far away, NMM cannot hear N11 sending messages because they are too far, and the power decreases with a quadratic law with the distance. So if they are very far, they cannot communicate directly. Right? So I invite you to go and look at the. I read this page because it's not very difficult and explains actually quite decently how does it work and why this happens. So it all depends on these circles, of course, which is the communication range. So, for example, if you consider wireless sensor networks, nodes in wireless sensor networks, there the power is quite low. And so the communication range is a few meters, like, I don't know, 10, 20 meters, depending on how much power you put in the communication. And so if you want to cover 100 meters, of course, it's not enough one single hop. You have to go 2 hops. But if you go 2 hops, the one in the middle suffers from the hidden node problem for sure, because A cannot go directly to C, so he has to send to B. And then C, if he wants also to send to B, runs into problems. Even when C wants to send to, I don't know, another one, like D, will be into trouble with A. So if A wants to send to B and C wants to send to D, well, you are in trouble because they are going to interfere on B again. So again, I don't want you to avoid this problem. There are techniques for avoiding that, but I don't want you to solve the problem. I just want you to show the problem exists. Okay, guys, I have to go now. So we can continue tomorrow. So if you have more questions about the assignment, please just make a list and we will continue to discuss in the next days, starting from tomorrow. Okay?
Professor, only a formal question about the course. It's right what is written on Detailed Active. The deluxe lecture will be not the next week, but in 2 weeks. The course will end.
So yes, I'm trying to follow the calendar. So I don't have too many things to do, but I will stay until the end. I mean, how the calendar is. I will follow the calendar. So if we finish our lectures before that, I will stay anyway, just to, for example, discuss the project or to work together and doing exercises.
Okay. Grazie mille.
Okay. So bye bye. See you tomorrow.
Bye.